Arizona State University and Science are recognizing researchers who address pressing problems. The ASU Science Prize for Transformational Impact honors early career scientists developing innovative solutions to today's biggest challenges. Hear from the inaugural winners on ASU's Lab Coat Optional podcast and visit science.org/ASU to apply. This podcast is supported by the Icahn School of Medicine at Mount Sinai, an international leader in research, education, and patient care. The school is the academic arm of the 7-hospital Mount Sinai Health System in New York City. It is consistently ranked among the top recipients of NIH funding. What are researchers in genomic medicine working on to transform patient care and improve patient health? Find out in a special supplement to Science Magazine prepared by the Icahn School of Medicine at Mount Sinai in partnership with Science. Visit our website at www.science.org and search for Frontiers of Medical Research-Genomic Medicine. The Icahn School of Medicine at Mount Sinai. We find a way. This is the Science Podcast for July 2nd, 2026. I'm Sarah Crespi. First this week, scientific relations cool in the Arctic. Senior international correspondent Rich Stone talks about rising geopolitical tensions and the effect of these strains on scientific collaboration on the Norwegian archipelago, Svalbard, which has been at the forefront for climate research. After that, producer Megan Cantwell talks with researcher Thomas Gernon about how Antarctica got its ice sheets during a time when the temperatures were relatively warm. I've spent a lot of time talking to reporters and scientists about research going on in Svalbard. This is an archipelago that is part of Norway. There's a ton of science happening up there. I've heard about the microorganisms that have been locked in the ice for thousands of years that will definitely not turn us into zombies when the ice melts. Often people who go visit will say, oh, yeah, when we leave town, we have to bring guns because of the polar bears. That's classic Svalbard small talk. And then, there's a ton of research being done on the accelerated effects of climate change in this part of the world. Rich Stone, our senior international correspondent, is here to talk about how some rising international tensions are affecting collaborations on this scientific archipelago. This work was supported by a grant from the Pulitzer Center. Hi, Rich. Welcome back to the podcast.
Hi, Sarah. Great to be back.
What was it like visiting?
It was interesting because when I arrived, there was a warm spell on Svalbard. So everything was melting and the snow was impassable by snowmobile because it was too soft. And there was meltwater rivers that were not traversable by snowmobile. So it's really frustrating for me and for the scientists when I first arrived there. Then there was a cold snap and a blizzard, basically, and everything froze back up. And the scientists were like, great, we can finally get back out and do our research. It was so cold. It was so windy and so cold. But for the researchers, like, yes, they weren't trapped in their research stations.
I kind of glossed over what I think of as the highlights of my of the science at Svalbard. What do you see as kind of the notable research efforts coming out of this place?
Well, Svalbard is really on the frontiers of climate change. The Arctic is warming much more rapidly than temperate areas, but Svalbard is the Arctic on steroids when it comes to warming. It's warming even faster than the rest of the Arctic. So you have this microcosm of change playing out really rapidly in Svalbard. It's keeping scientists busy trying to keep up with the changes going on there.
So Svalbard is part of Norway, but it has kind of this international flavor to it because there are so many research outposts, research stations there from a dozen countries or something like that. How did it end up kind of becoming this place where so many people end up doing science?
Svalbard has such a cool history. It was a no man's land until it was discovered by Willem Barents about 400 years ago. And then whalers started using it as an outpost. No countries claimed it for centuries, essentially, until substantial coal reserves were found there. Once it became a valuable strategic resource, countries were like, oh, yeah, we were there first, maybe. And then it was worked out through negotiations that resulted in the Svalbard Treaty. And the Svalbard Treaty awarded Norway sovereignty over Svalbard, but it also had a provision where any country that was a signatory to the treaty, that citizens could come and work there, live there freely, and it had a provision for research as well. It foresaw the value of doing research on Svalbard.
There is some kind of political tension playing out in that relationship due to some of the geopolitical shifts that are happening globally. Can you talk a little bit about some of the pressures that are being applied?
Even in the midst of the Cold War, Svalbard was this relatively stable, peaceful place where countries got together and did research. The tensions have really started to rise more recently. It's partly a result of the Ukraine war and tensions between Europe and Russia. Russia is one of the treaty signatories. It has a mining community in Barentsburg on Svalbard. It has a former mining community called Pyramiden that is just maintained as a little like tourist outpost right now. And Russia has been active in research on Svalbard.
What changed when the war came?
Cooperation. Cooperation has essentially ground to a halt because of the Ukraine war. That's one point of tension. The other point of tension is China's aspirations in the Arctic. China has grand ideas about creating a polar Silk Road.
A polar silk road. What does that mean?
A polar Silk Road, collaborating with countries on communications and shipping and so forth. There's an anticipation that because of climate change and warming, the Arctic Ocean is going to be largely ice free within a few decades. And so there's going to be anticipated to be shipping routes through the Arctic. And so China, the countries see the opportunity for shipping routes. There is potential for mining and whether that would take place in international waters. Norway has done its own mapping of mineral resources in its territorial waters. So there are these strategic opportunities that are opening up, but also countries like Norway are quite concerned about Chinese and Russian influence and spying in the high Arctic. That has been a point raised by Norway's intelligence community, for example. So there's a lot of wariness that has really developed.
It does seem like when tensions go up, all these useful collaborations that scientists involved in suddenly become suspect, and we see that happening in the US too.
They certainly come under scrutiny. Norway takes great pains to say that while it is the sovereign nation that oversees Svalbard, they don't want to impede good science, but they are under pressure themselves. The US Congress, a couple lawmakers in 2024 expressed concerns about some of the research going on Svalbard that China was doing. There's a defense related institute, a radio wave propagation institute, that was doing space physics up on Svalbard. And Congress was worried about the potential military applications.
It has kind of unusual access to space, both because of the long nights and also because of the auroras and also because of polar satellites that could be kind of constantly in contact with this area. So there is some space science going on, as well as the glaciology and climate change. Now, we've talked about like the tensions and the suspicions. What has changed about collaboration or the ability to do science in this place?
Well, right now, the changes are subtle. Research is coming under heightened oversight. There's a new Svalbard research office that just opened this past spring. There's a new regulation that's going to require scientists to hire registered Norwegian guides when they do research. That some scientists say is aimed at trying to keep better control of what Russia and China may be doing. China is partnering both with the Norwegians at Ny-Ålesund, the scientific outpost, and with Russia in Barentsburg. They've agreed to cooperate with the Russians there. So the Norwegians really would like to be able to keep tabs on all of the research going on Svalbard. And one mechanism may be this new provision requiring a research guide.
The downside of that, of course, is that you have to pay someone that works for Norway while you're doing your own research.
Guides are not cheap. It can be a prohibitive expense for some, especially European scientists who are working on pretty tight budgets, and especially scientists who know Svalbard very well. They've been going to the same field sites year after year, and they're like, why do we need a guide?
You also mentioned in your story that there's some restrictions on what's going on with the sea, too, like how people are able to access the sea surrounding Svalbard.
This is a recent regulation. actually a prohibition on mapping of the seabed in territorial waters of Svalbard. It used to be de rigueur for scientists to be able to do these bathymetric surveys, hydroacoustic surveys, and now these are largely prohibited.
Bathymetric means like topography under the water.
Yeah. And it was used recently in the discovery of these underwater methane seeps that could be releasing substantial quantities of methane into the atmosphere.
And as you said, this is kind of this like microcosm of the future of climate in the Arctic. It's the fastest moving climate change model we have right now. And not being able to study it in the moment is not great.
For the climate researchers, it's like having a hand tied behind their back. They will love to be able to have this fuller picture.
I know Russia has access to the Arctic. Does China have another way to access the Arctic and do science? Is this kind of their go to?
Svalbard is their major entree into the Arctic, apart from any collaboration they might be able to get going with Russia bilaterally. I mean, Russia has about 50% of the Arctic coastline running the length of Siberia. But in terms of the ability for China to conduct real research, a lot of it is going on in Svalbard. And China's also interested in getting involved in this new polar drift station that France is launching next month. It's called Terra Polar Station. China's not involved in the first expedition. It's a overwinter drift that scientists are excited about, but China wants to get involved in that down the road. And so it's looking for ways that it can access Arctic research. At the same time, China has a very substantial Antarctic research program. It puts a lot more emphasis down there. But every major political power sees the importance of the Arctic as the climate changes and as the Arctic becomes more accessible, and everybody wants to stake their own positions there.
You mentioned pressure from Congress people in the US on some of these agreements that Norway is involved in Svalbard. But is there an other element of the US in this story?
Yeah, I mean, the US doesn't do very much in Svalbard. There's a few American scientists there affiliated with other countries' programs. America does not have a research station in the Allison like some other countries do. Most of the American research in the Arctic takes place in northern Alaska. But America does have interests in that region. There's a US military base in Iceland, for example. There's obvious sensitivities about China conducting potentially military related research in Iceland. So that's kind of where the US congressional angle is.
I really don't understand this part of your story about these stone lion statues that ended up outside of a Chinese facility at Svalbard. What is this about?
So when China started leasing one of the buildings in the Allison for its own research station called the Yellow River Research Station in 2004, the Chinese authorities plopped these two stone lions, 1 ton each, stone lions on either side of the entryway for the station. It was meant, according to the Chinese scientists there, as like good fortune, good luck, ward away evil, etc. So they've been there since 2004, and nobody really seemed to mind. Just a few years ago, 2024, tourist ship came, and tourist ships do visit Ny-Ålesund in the summertime. And the Chinese tourists on this boat were there to celebrate 20 years of the Yellow River Research Station. They were waving Chinese flags, and one of the people was dressed in a Chinese military uniform. Norway reacted quite negatively to that kind of exhibition of nationalism and demanded that the Chinese remove the stone lions. They didn't want a symbol of China or any other country, that kind of visible symbol standing out in the Allison. They wanted to homogenize it as a Norwegian research station with various other countries as collaborators. They demanded the Chinese remove the lions and the plaque identifying Yellow River Research Station as a Chinese station. Just earlier this month, the Chinese did remove the lions, and the plaque was replaced with a plaque designated it as part of the Ny-Ålesund Research Station.
All right, Rich, thanks so much for talking with me.
Sure. Happy, Sarah.
Rich Stone is a senior international correspondent for science. You can find a link to the story we talked about at science.org/podcast. And a reminder, This work was supported by funding from the Pulitzer Center.
Want to elevate your travel experience? Here's how. With a Delta SkyMiles Reserve American Express card, you can relax before your flight in the Delta Sky Club with up to 15 visits per medallion year. And now through July 15th, 2026, you can earn up to 125,000 bonus miles, so you're closer to your next adventure. The Delta SkyMiles Reserve card. Check out the new design at www.delta.com/Spotify. Minimum spending requirements and terms apply.
This episode is brought to you by Perfect Bistro Cat Food. Cats, this ad is for you. Has your human ever called you picky, persnickety, choosy? If so, Perfect Bistro Cat Food is for you. With ingredients like wild-caught tuna and pasture-raised lamb, tantalizing textures, and delectable flavors that meet even the most discerning cat standards. You're not picky, you're just perfectionists. Perfect Bistro, mealtime perfection for every cat. Have your human visit perfectbistro.com.
Also out on the site this week, I want to call attention to kind of an epic moment. Dan Clary, staff writer here at Science, writes that the Rubin Sky Survey has begun. The Rubin Observatory begins its 10-year movie of the changing universe this week. Also on the news site from freelancer Sam Keen, we have a story on the retraction of two papers by Max Planck. He may sound familiar. There's a constant named after him. He's a legendary pioneer of quantum mechanics and the 1918 Nobel laureate in physics. These two papers were published in Springer Nature Journal in the 1940s and retracted quietly in 2011. Sam looks into why this might have happened, and it looks like it was probably flagged for being replicated elsewhere on the internet, which was not a problem when the papers were published. Really interesting look into this mystery. From the commentary section this week, we have a trio, three policy forums on U.S. science history, celebrating the 250th anniversary of this country from the lens of science. Brad Weibel, our editor for Policy Forum, writes, the history of science and invention in the United States is punctuated not only by fundamental discoveries and technological breakthroughs, but also transformational policies, practices, and institutions. Much of what we recognize as the modern science and innovation system has deep roots in how universities, industry, and government evolved over many generations. And so, yeah, really interesting policy forum, all these different lenses to look at how science changed over time by looking at universities, industry, and government. Last in this roundup, I want to call out something from the journals. We have a Science Advances article by Bouchot and colleagues titled Community Notes Under Moderate Polarizing Content by Design, Creating Risks in Electoral Processes. This is about those little audience-generated notes that appear on social platforms, in this case X, that on the surface are intended as a correction to misinformation that gains popularity. But this paper suggests that corrections with support from both sides get more audience endorsement, which doesn't mean that they're actually dispelling misinformation. Okay, back to the show. Next up, we have another story from the poles, this time the South Pole. Producer Megan Cantwell talks with researcher Thomas Jernan about the role of continental uplift in the glaciation of Antarctica.
Earth has gone through many glacial cycles, but one process that's puzzled researchers for quite some time is exactly how Antarctica became glaciated. Around 34 million years ago, big ice sheets started forming on the continent during a relatively warm period. The predominant theory for what could have driven this growth has some gaps, and this week in science, Thomas Gernon and colleagues come up with a model that might resolve a few of these big questions. Thank you so much for joining me, Thomas.
Thank you, Megan.
I thought first it'd be a little helpful to sort of lay out exactly which ice sheet we're talking about here. There's two separate ice sheets within Antarctica.
Yeah, so the East Antarctic ice sheet is the oldest and largest ice sheet on Earth today. And so it formed around 34 million years ago. It's of such a scale that if it melted, sea level would rise by about 52 meters globally on average. In comparison, the West Antarctic ice sheet is smaller in scale, but it's more vulnerable in some ways in West Antarctica because a lot of the ice sheet is below sea level. And so there's wet-based glaciers and ice sheets which can effectively erode more.
And so in terms of the formation of the larger East Antarctic ice sheet, how do researchers know that it was around 34 million years ago? How did they sort of constrain that?
When an ice sheet grows, we have a big change in oxygen isotope ratios, and we see a steep decline around 34 million years ago. Basically, the heavier delta 18O goes into seawater when ice forms, because the lighter 16O preferentially goes into snow. But actually, in our work, we find that maybe as early as 40 and potentially within uncertainty, even 45 or 50 million years ago, we had some ice assembling in probably high elevation parts of Antarctica.
Not as widespread, but sort of the seeds were beginning.
Yes, exactly.
In the past few decades, what have researchers thought have kind of driven the growth of this ice sheet, particularly at the sort of 34 million year mark?
So over the course of the Eocene, which is the geological period, the end of which the East Antarctic ice sheet arose, we had this tumble in CO2 concentrations going to around 600 or 700 ppm at the Eocene-Oligocene transition. For example, 50 million years ago, the concentrations of CO2 in the atmosphere were about 1,600 parts per million, which is just under 4 times what it is today. So it's clear that there was a large-scale, long-term decline in atmospheric CO2, and that's been traditionally seen as the kind of smoking gun.
What have been sort of the gaps in just CO2 declines alone explaining this widespread glaciation across East Antarctica?
One of the major mysteries is that if atmospheric carbon dioxide is the only explanation for the Antarctic glaciation, we would expect maybe to see both hemispheres forming ice sheets. We don't actually see land ice forming in, say, Greenland for at least 25 million years after Antarctica. So there's this sort of discrepancy between the North and the South hemispheres. It kind of suggests maybe CO2 isn't everything. And the other interesting observation is we know from sea surface temperature records around Antarctica in the high latitude Southern Ocean that the temperatures were actually surprisingly warm in the ocean for possibly over 10 million years after the emergence of the continental ice sheet in Antarctica. And this is kind of contrary to what you might expect. It's a major sort of enigma why we had unexpectedly warm temperatures when the ice sheet is actually around.
What could sort of explain this gap? What else could have helped driven the ice sheet nucleation?
When you actually boil it down, they come down to tectonics, plate tectonics in some way or another. For example, the uplift of the Tibetan Plateau, which effectively erodes lots of rock quite quickly and weathers that rock, and that effectively then draws down CO2 from the atmosphere, and we have global cooling. The other appealing explanation is also related to global plate tectonics. We're thinking about very long-term geological processes, tens to hundreds of millions of years. Antarctica was once part of a united landmass known as a supercontinent, which was called Gondwana. And the breakup of Gondwana started in the Jurassic. In fact, Antarctica sort of unzipped away from southern Africa. We had full breakup nearer to maybe 160, 150 million years ago. But this process didn't really kind of end until recently, geologically speaking, when we had various oceanic gateways open, such as the Drake Passage between South America and West Antarctica. Once that passage opened up, it allowed basically ocean circulation to pump almost like a coolant, pumping cold water around the continent. So that sort of isolated Antarctica.
You mentioned during the Jurassic, it's beginning to break up, but then we're seeing this glaciation 34 million years ago, right? So what is sort of the progression there?
This breakup process that happened 130 million years earlier than the glaciation itself. So it's a really long-term process. What we didn't realize before is that after rifting, these convective instabilities actually propagate inboard of the rift at a rate of around 15 to 20 kilometers per million years. That upwelling gives us kind of sustained high topography. So it's a really highly organized, and most importantly, it's a really persistent geological process, but it's kind of hidden, because it's happening beneath the surface. We generated landscape models in our study, which can very adequately reconcile this landscape whereby we have this steep marginal escarpment at the edge of the continent. We have this high elevation plateau. And then, given that this wave is happening quite slowly, we get this sort of culmination of uplift in the Gamburtsev Mountains around in the Eocene period. But we're having this peak kind of erosion pulse and uplift of this critical area of Antarctica, which is the high elevation mountain belt, just at the point when we think the cryosphere is starting to emerge.
So it seems like there was sort of a threshold height that this plateau had to meet in order for the ice sheets to spread across the continent. When in your model did it sort of reach this elevation that was likely high enough to sustain these ice sheets?
When we use these landscape models to reconstruct the topographic evolution, we're effectively reconstructing this lost world, frozen in time. We incorporate those landscapes then into an ice sheet model called PISM. This ice sheet model basically allows us to grow the ice sheet at different points in time, depending on the topography and how it's changed. What we did in those models was we fixed the climate conditions. And the reason for doing that is that we want to understand how sensitive ice sheet growth is to changing topography. We find that we have a tipping point, like a threshold for ice sheet nucleation, which happens around 45 million years ago, whereby we see a complete change and growth of the nucleation of the ice sheet in the Gamburtsev Mountains. It's becoming more and more stable due to the increase in elevation, the simple lapse effect, whereby the temperature decreases like by 1 degree for every 100 meters of elevation gained. So very small changes in elevation we were seeing in the models were having a really big impact on the climate.
So is it likely that the decline in carbon dioxide also still played a role, that during that period in time, there was enough of a decline for it to spread?
Yeah, absolutely. So we find that at a point around 40 million years ago, you get this kind of perfect storm, if you like, when the landscape levels have risen and the global temperatures have fallen and they've met in the middle. And we get the ideal mix of conditions to form continental ice sheet.
You mentioned how slow this process of uplift is as these waves are traveling. You said like 20 kilometers per million years. When did uplift of this sort of plateau region actually end in Antarctica?
It's very hard to say. So it must also be noted that we had active uplift in 2 of the other primary nucleation sites of the East Antarctic ice sheet, which are the Drawling-Maudland escarpment that I discussed a while ago, and also the Transantarctic Mountains, which are another enigmatic, very high elevation mountain belt that extends for about 4,000 kilometers along the sort of edge near the South Pole of Antarctica. So there's a lot of uplift that's happening simultaneously at around this point in time. It has been suggested in a classic paper by DeConto and Pollard in 2003 that the ice sheet originated in these 3 regions, that you had these 3 sort of bullseye-like nucleation centers of ice that could then at some point coalesce and form a much bigger ice mass. It's almost the perfect scenario for an ice sheet because it's not just the polar latitudes that are cold naturally, but it's also high elevations, and at the edges of this saucer-shaped kind of region prevents some of the ice leaking or escaping, from the continent or from the plateau. The conditions needed to grow a continental ice sheet are extraordinarily specific. And this process of forming an ice sheet took geologic time to assemble. Over future millennia, as ice sheets melt and change, you have, really serious levels of erosion caused by that process. So the glaciers that are liberated and the ice sheets that basically break apart, they modify the bed surface that they're sitting on. The conditions needed to regrow the ice sheet will be completely different in the future. So rather than the paper just being about maybe, how the ice ages start, it's kind of like, here's why once it's lost, it's not very easy to grow back in the same way.
This modeling that you did, how does it compare to previous models when they were looking at how the ice sheets might have spread?
In the past, I suppose paleoclimate studies have maybe discussed the role of uplift regionally in Antarctica, but perhaps not really thought through this long-term lens. So I think hopefully our study really gets that across, that there is a very long-term uplift processes that are quite important to consider in these models. The other really interesting factor about the Gamburtsev Mountains is that when you're so near the South Pole, you get very little sunlight. So all through the year, you find that the incoming solar energy is quite a low angle. What that means is when you have alpine topography, ice can kind of get trapped behind some of these rocky peaks, and that ice may not see sunlight year round. We figured that this ice trapping effect could be important, and this is something that we incorporated into our energy balance model situation. What the energy balance models show us is how this interplay of climate and uplift play out together.
There's just clearly so much work that went into fine-tuning this model, looking into this sort of new mechanism for uplift happening over a longer period of time. Are there other parts of the world that you want to look into, that other mysteries kind of to resolve through a similar lens?
Yes, absolutely. I mean, it's also really interesting to me that Greenland, for example, is the other major ice sheet, which is in the northern hemisphere, only really started, growing properly in the last 5 million years, arguably maybe 10 million years. So a long time after Antarctica. But equally, the east coast of Greenland has high elevation topography. I'm not saying it's formed in exactly the same way, but it's interesting that there is this high elevation region. And it has been reported that a large degree of uplift has happened over the last 40, maybe 30 million years in the northern hemisphere. Maybe that there's this really finely tuned orchestra whereby, the south and north are actually responding to very slow processes of uplift that was set about in this kind of almost chain reaction way much longer ago. And that's a kind of a tantalizing prospect, and one that I think would be really interesting to follow up on in the future.
Yeah, I look forward to seeing that. Well, thank you so much for taking the time to speak with me. I really appreciate it. Thomas Gernon is a professor of earth science at the University of Southampton. You can find a link to his paper at science.org/podcasts.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions, write to us at sciencepodcast@aaas.org. To find us on podcasting apps, search for Science Magazine. Or, as always, you can listen on our website, science.org/podcast. This show was edited by me, Sarah Crespi, and Megan Cantwell. We had production help from Podigy. Our music is by Jeffrey Cook and Wenkoi Wen. On behalf of Science and its publisher, AAAS, thanks for joining us.
Hey, it's Ryan Reynolds here from Mint Mobile. Now, I was looking for fun ways to tell you that Mint's offer of unlimited premium wireless for $15 a month is back. So I thought it would be fun if we made $15 bills. But it turns out that's very illegal. So there goes my big idea for the commercial. Give it a try at mintmobile.com/switch.
Upfront payment of $45 for 3 months, $90 for 6 months, or $180 for 12-month plan required. $15 per month equivalent. Taxes and fees extra. Initial plan term only. Greater than 50 gigabytes may slow when network is busy. See terms.